but then she talks more than I do. So it is a tough fight. And so we should recap and see where we go from here. Now, this officially is a tutorial, 2 hours, okay? But my tutorial from the beginning was meant to be like this. I gave you from the beginning all the material and more than we covered in the class, because I wanted to invite you to browse through those things and search for what you find more interesting for yourself. Okay? I did not want you to follow a precise scheme because I have decided you should do that, you should do that. Because it is not even possible in 1 week, and not knowing what are your backgrounds. So today's tutorial will be like this. I'm not going to tell you more of what to do. I tell you that we spoke about the Langevin equation, and so you can look also at the code on the Langevin equation, which is something we haven't looked at so far. So far, we have not looked at the construction of a measure for a continuous dynamical system. There is a code, which I think is the one that is called the simple Euler ODE, where I use an integration scheme, which is Euler scheme. It is very simple, and that computes the response, the evolution of the expected value of a given observable. I gave you the formula for this evolution already in one of the first classes. But then, going through the subsequent lectures, things should have become more clear. This, maybe I write on the board the formula what it was. It is that the expectation time t of an observable O is equal to the expectation time 0 of the same observable O plus an integral from time 0 to time t of the expectation time 0 of the observable O composed with the time evolution up to t times what we define as the dissipation function, sorry, up to time s, integrated by ds. This is called the formula of exact response. And here there is something important in terms of coding. That is the fact that you have to compute this expectation. Now, this expectation, in fact, is a correlation function. Okay? Is a correlation function of the observable O at time s with the dissipation function omega. So it enters among the things that we discussed today. How do you compute this correlation function? Well, you need to generate if you do it numerically, no, I'm not going to switch it on today, yes. You have to generate the ensemble of initial conditions. Because an expectation, if you can compute it analytically because you know the initial distribution, and then this distribution and the functions themselves are sufficiently simple, then you can do an analytical calculation. And in my handwritten notes, and also in the other exercises, there are some analytical calculations of this sort. In particular, for the simple system that I want you to study. But suppose that things are more complicated. What do? Then you have to rely on what is called an empirical distribution. not a theoretical one. An empirical distribution means something that you get in your hands dirty. Okay, you go in and pull out. And so, in practice, an expectation is associated with an average over a certain number of events or samples. Okay, so numerically, if you cannot do the thing analytically, I tell you, in the example that I give, you can do things analytically, but that's about the only one case in which you can, very few. In general, you have to do something empirical. So, how do you create the ensemble? It was good. I didn't connect my laptop. You have to have a random number generator. Okay? And so, in the folders of the codes, I give you also one to generate an ensemble of a given form. Okay? Random number generators, usually they give you a uniform distribution. Okay? They pick up number at random with a uniform distribution. But your initial distribution may not be uniform, maybe something else, maybe a Gaussian, or I think what I have implemented is a triangular distribution, something like this. It is not uniform. The random number generator will give you a uniform distribution. Now you have to transform it into a triangle. So, in the folders, you find this kind of things. Go to the folders and do whatever you like. And if you have questions, you ask me. Okay? Take a look at the implementation of this formula. There are some tricky things that maybe you find out by changing parameters and things. Okay? It's not important how far you go. Just enjoy yourself if you can. If you do, I hope you do. For the rest, I'm here, okay, and I'm here still tomorrow, but tomorrow morning you have the exam. The exam, I don't know what they told you about, and it is a multiple choice. There will be some questions from my side and some questions from Professor Fatah's side. I tried to make it very simple, but if it happens not to be too simple, I apologize. And do whatever you can, because you know, in any case, they tell me that it is not good that everybody gets all right. This is what they told me. Don't say, huh? But I told him, Professor, don't worry, if they don't get all of them right, it's better. Anyways. So if there are too many fails, or if there are too many top, it means the test doesn't really distinguish. Okay? It is a whole science, this of tests, which is not my science. But in any case, I know, actually for some years in my career I had to look after also this kind of things. But I readily forgot. So, I guess that at least with my part, you will all do well relatively to what is considered good, which is not top and not bottom either. So don't worry, okay? Don't worry. If there is some issue, I hope that they ask me, and so I will fix the issues. So tomorrow morning there is this. In the afternoon, I think that they set up some meeting for me, so I don't know. But you can reach me anytime by email or other means. in the coming future. So for the rest now, in what is left of these 2 hours, you do what you feel like, go through the folders, look, even though you don't want to look at the codes, you want to look at theoretical aspects, do. And I'm here, you can ask me questions, and if you want me personally or in small groups, or also all together to tell you about possible applications, possible projects, I don't even know how many open projects I have. I don't know, because people come to me and then it is a new project, and then other people come to me and then it is a new project, then till the next month when the first person comes back, I don't remember that. What can I do? Just one. But we all find a way to move forward, okay? So if you have any other kind of curiosity, just come and ask, okay? So have a good afternoon and enjoy whatever you are doing. I'm here. So if you want to ask questions publicly, you can ask questions publicly. Yes, about projects, for instance, I just come back before, in the past 2 months or 3 months, I've been in various places where I met people who told me about problems that they would like to have help. For instance, in molecular biology or other kind of things, in which my techniques can be applied.
So any project related to machine learning?
Any project in?
Machine learning.
So, yes, there are. I'm not an expert of machine learning, but some of these techniques that I have used, people are importing them in machine learning, and in particular, some young collaborators of mine in my university, they are working on this in collaboration also with the University of Stanford, with the New York University and so on. So I can tell you what are the techniques. One is that formula that you have there. And then, if you like, get in touch with these collaborators of mine, because...
Sir, actually, I need a bit of idea that whatever you have taught us, so what can we use where?
What you can use where?
In aspect of machine learning, I'm asking that, let's say there is this formula, where it will be used, either in back propagation or
Yes.
cross finding or where?
So, now maybe some of you would be able to tell you better than I can, but there are these energy-based models in which the energy-based models and also machine learning as particle system and also diffusion models or something like that you may have already heard, where the reconstruction of your object function can be framed into a sort of dynamical system. I can show you some references on my laptop if you like. Then, once you write the problem, say you have your objective function f, okay, reconstructed as a certain approximation fn of a certain sum of functions with parameters that depend from certain other parameters from the variables, and then you have sort of basis functions but they are not the basis. Like, for instance, you know, there is a lot of ReLU, okay, functions that they constitute interpolants rather than a basis, okay? Then you can write equations for the evolutions of the parameters. They are dynamical systems. So you can investigate this, and then you hope that this goes to your objective function f. Then you can use the techniques of dynamical systems and also the techniques of probability. Why? Because, you see, this n goes beyond the number of points in which you know your function. Say you know your function in these 4 points. Now, suppose that the function is like this. How do you know? Okay, so you have to be ready to deal with expectation values and with probabilities rather than with the fully deterministic thing. And so in my group, people work on this and they use formula like this because this tells you what the average will go where you don't have time but you have the increase of interpolants. If n rather than being time is the list of interpolants, mathematically it is the same thing. Okay. Now this is all vague, I understand, but I can give you references and get you in touch with the people who do these things. But this is, I'm glad that you asked, because machine learning, artificial intelligence are a very big field these days. I'm happy to see that they want to learn techniques of what is my specific field. You know what is my specific field?
Statistical physics.
Even more specific, not many people know. Non-equilibrium. Non-equilibrium statistical physics. Okay, and I'm glad to see that people want to use the techniques that are developed in this field that starts with Boltzmann. Okay? So, just to give you an idea, that what I told you, I didn't speak of applications. But you name an application, and I tell you that there is possibility of doing something.
Sir, let's take an example. Let's say I want to have a new loss function.
Yes.
So how can I can use?
Yes. Yes. The omega plays an important role in that respect. The omega becomes what is known as a large deviation function. Okay, something that you stick in what is called a Kullback-Leibler divergence. And you can use it but this now you have to ask those who do it. You can use it to implement a smart, presumably, loss function.
Could you repeat that again? I mean, which function?
So this is called, but look, these things are still not even in the literature. There are some things that are being developed, but omega is a large deviation functional. I mean, this is what we are finding out these days. I'm working with my people to show that this is a large deviation functional, which is the universal function that allows you to describe a probability distribution in its extreme events, in details. Okay? You know that there is a central limit theorem that that the distribution near the mean is approximately Gaussian. But what happens when you go away? Well, you can write your probability as e to minus n, a certain large deviation functional, okay? And in the limit that n becomes infinitely large, this goes to this asymptotic function. Now, these are used in many things, for instance, to study the temperature fluctuations of the Earth. But there are many events that are too far from being Gaussian. Gaussian leads to diffusion. It is a very limited set of events. They are so chaotic they cannot be realistic. Okay? They are like tossing a coin with probability half and half. That will give you, in the long run, will give you a Gaussian distribution. But in general, if you have events that are repeated more or less randomly, like it would be as you evolve this equation under certain rules, okay? This fast decay of correlations, that is the same that you have in the Langevin equation, doesn't take place. So you need to know, okay, even for IID variables, the peak of your distribution will be a Gaussian. But the tails may be more important than the peak. How do you describe the tails? You describe the tails with large deviations theory. Large deviations theory is based on a large deviation functional, and as far as I understand, but this I should ask one of my postdocs, precisely what it does. But he has surely written it on a tutorial that he has put in the archives recently. Okay? The dissipation function can give you a hand to have an efficient loss function, which I'm telling you in words. I don't know precisely the details. But if you want, if you have internet open, I can show you. Search. This is PhD thesis which he defended the last year. And he gives you the ground of things that I told you. There isn't, in terms of techniques of non-equilibrium statistical mechanics, there is only a limited amount, there is much more. But this gives you the idea. And also some of the references to energy models, to machine learning as particle, as particles. But when we get there, I show you the cited literature on what you should look at. But if you start with this tutorial that he wrote, I received a lot of positive feedback because he's my student and people tell me that I've been good, but he has been good. I still do it. This kind of systems, they have to develop specific techniques whenever they change a minimum degree, because there is at present no general theory. Okay? The general theory, what you would do, well, you would describe the evolution of the probability data. And because this is an algebra-like equation, apart from this. Okay? And there is a Fokker Planck equation where, unlike what I showed you earlier in the morning, because of the delay, you have to integrate the D1 there, what I call D1, has to be integrated over the points that you have around the lambda. Now, I have developed a general theory, but this general theory has not been adapted to equations in 2 days so far. So she tells me, but not only her, a number of people, but in particular I'm happy to have collaboration, that if I can develop my theory for this delay equation, then it would be very, very beneficial to them. And then they do all sorts of beautiful applications. This is very theoretical. And then I think this one goes also to some biological application. In any case, just from the title, you see. So, if you, the group of you, are interested in this kind of things, I can show you what my references, what I've done so far for equations that have no value. And then it would be very nice to apply to the problems of salinity. Sure. Yeah, I think she takes a finite delay. Yeah. A finite delay, but no particular restriction, not particular short. Okay, this we have to find out from the various papers. I think she considers different situations. Yeah, generalize. Yes, that I know. I have not worked. Because this project, I know that it's quite hard. I know, you're right. And in fact, because you see, you go from a differential equation to an ordinary, to an integral. It is much more complicated. It's like the Boltzmann theorem. And then you have to invoke all sophisticated mathematics. But on the other hand, what I've done is embedded in that formula up there for stochastic processes, maybe can be developed, okay, because no, not yet, but I will try. But I need workforce. If you can provide the human resources, that is very good. You see, the difference between what I do and what most people do is that because the problems are difficult, they turn to approximation. The simplest approximations are linear. Okay, you do a perturbation and then you expand up to a certain level. Now, what I have developed with my colleagues from Australia, Brisbane and Cameron then it becomes even a little more complicated. But in this paper it is done, as long as there is no delay. Now, I'm pretty sure that one can rewrite things in such a way that it works. Questo fa strutture stazze, distribuiremo Harun and Lee. What we can do, no, start right.
Get ready for
What they do, they try to do statistics. This equal, and they try to build a Gaussian statistic. Because that is what people don't know. This Gaussian description hides the large deviations, what I call which are becoming more and more common. They are not captured by the standard analysis. People know that there are, but they mostly with us. Now, if you try to average things when fluctuations are so much larger not having it is the type of thing. Other ways of discussion are quite effective when you get periodic band. There is no instance to do real mode. Then you can or the time step steps. This I think is a
हाँ जी सर चलेगा कर दे कर दो बस कर सकते फालतू में चलो